Okay, once again, you are mostly welcome to this platform. We are going to look into the marking guide of Uneb Uce 2024 Physics. Okay, so let's now kickstart. Okay, well, before we go into the items, let's look into the instructions they gave us. So the paper code is 535 stock 1, physics paper 1, theory. And please, this is the first paper of physics, new curriculum as far as Uneb is concerned. The paper lasts for 2 hours and 30 minutes. Let's go through the instructions. So instructions to candidates. This paper consists of 2 sections, A and B. It has a total of 7 examination items, or sometimes we call them areas of construct. Section A has 3 compulsory items. Section B has 2 parts, 1 and 2. Answer 1 item from each part. Then that means that in total you answer 5 items in all. So here, out of the 7 you attempt 5 items, and that means that out of the 7 you leave out 2. So still they say any additional items, but let me get this. Okay, here they're saying any additional items answered will not be scored, meaning that you get no mark for any item added. Answer to all items must be written in the answer booklets provided, or graph paper. And the graph paper is also provided for you. So with this, I'll not go through them because I know it is this one of answering all the items on the answer booklets. I know the answer booklets are provided, and each one of us knows that the graph paper are provided especially by Uneb. Let's now proceed. Okay, now I think let's start off with item 1. So item 1 said, and this is part of section A where they say that it is compulsory section. So still the rule tells you answer all the items in this section. Okay, item 1, they're saying in a classroom activity, senior 3 students of your school are presented with the learning aids shown in figure 1A, 1B and 1C. Now figure 1A, we are seeing a figure of that kind. You can all see that. Figure 1B, you can see this. So figure 1 you can see, figure 1B is this one, and figure 1C you can see from here. Figure 1C is this graph. Alright, so let's proceed. What they want. So now they're saying, okay, the students are required to part A, Roman number 1, describe the formation of the phenomenon shown in figure 1A in a classroom setting. So that's the first thing. They want you to describe the phenomenon shown in figure 1A in a classroom setting. Okay, Roman number 2, explain why the physical rainbow appears. Okay, we saw rainbow somewhere. Explain why physical rainbow appears curved as shown in the figure 1a, and why it is in the position opposite to where the sun is. Great. Part B, state the general name of the waves shown in figure 1b. Shall be seeing that. Explain the effect of the two radiations at the extreme ends of figure on a photographic plate. Shall still see that. Roman number 3, explain the usefulness of visible radiation. Okay, we shall see that still. Roman number 4, explain the pattern of the wave shown in figure 1b. Alright, then part C, use the figure 1c to determine the amplitude of the sound waves, frequency of the sound waves. And I guess that marked the let's go and see. Okay, well, they want us to answer that. Let's move on. Now the thing, the senior 3 students are unable to do classroom activity due to lack of knowledge and have approached you for help. A task, assist the senior 3 students to do the classroom activity. Okay, now the classroom activity, just to remind you please, this is the classroom activity from here. The classroom activity given to them starts from here up to there. That's the classroom activity they have. So we shall all also follow activity per activity, like from Roman number 1 part A, Roman number 1 part B, Roman number 1 part C to the end in every case, and then we see the way forward. Okay, good. So let's first go and analyze what is that part A. Let's start with part A. Let's start by answering part A. So part A says it's here. Okay, maybe I can raise off this. Okay, great. Okay, he's right. So the saying, describe the formation of the phenomenon shown in the figure. Now the word phenomenon means it is a natural occurrence. It is a natural occurrence. It occurs on its own. Okay, phenomenon shown in figure 1a in a classroom setting. So they want us to talk something or say something about the phenomenon in figure 1a, or that natural occurrence in figure 1a. We describe it in classroom setting, that besides the natural occurrence, how can we present it locally in class. Let's go and see what it is about. It was 1a. So you realize that the phenomenon they want us to talk about, is this. It is this one here in the picture, and what you're seeing there is a rainbow. So now they want us to describe what a rainbow is in a classroom setting. But what should we know about rainbow? A rainbow forms what we call the Roig-Biv colors. Roig-Biv, like this. Roig-Biv colors, please. I guess you all know this acronym, the Roig-Biv, whereby R is for red, O is for orange, this is for yellow, this is for blue, this is for indigo, and this is for violet. So you must also think, where do you think we have those colors? In the physics you learned, where do you think we can have these colors here elsewhere apart from the natural occurrence of the rainbow? Where else can we see this in our physics? So you realize that where we can see that possibly it can be when you have used a glass prism. Let's go there and see. Okay, well, let's start off. So we are saying that the phenomenon is a rainbow. We have all seen that from the picture. Okay, well, now let's get our glass prism. Let's get a glass prism and we see how we can form the Roig-Biv colors. Let's see how that can come about. So first you realize that we have a source of white light which is incident onto a glass prism, and then what must you expect here? Once a source of white light is incident on the glass prism, then what you must expect is there will be some refraction like that, and then these ones will be given off in that order. Then another one be refracted in that order and will give off, be refracted towards the base. You all know refractions at the glass prism, they are refracted towards the base. This is what you are calling the base. Okay, good. Now you realize that as these light rays spread, they are very many in number, very many in fact, but specifically here we shall say they are 7. Just imagine they are 7. But to begin with, from the word Roig-Bev, from the word Roig-Bev, from the word Roig-Bev, you see this? From the word Roig-Bev, you realize that at the first extreme part up we have red, and the last part we have what? Violet. So for us we shall concentrate there. So this is our red R, and the last one is violet. Okay, and now that's what you're going to form. We're using a glass prism. So the glass prism setting on how we can see the rainbow, but in the rainbow we look for those Roig-Bev colors, which is red, orange, yellow, green, blue, indigo, and violet. We can easily see that when we use a glass prism and we allow a source of white light incident on it. Once the source of white light is incident on the glass prism, it will be refracted into 7 different colors, which are the Roig-Bev I've already talked about. Let's see. So I think you can see the behavior of every light once this incident. You realize that from here, once this light comes in, the red comes. Well, I try to at least bring out the color such that you can easily understand. I put the respective colors there. Okay, from the Roig-Bev, you see that this is a red, this is orange, this is a yellow, this is green, like that. I try to at least bring that out, and you see that once they are incident here, they are refracted, and they are refracted at this point. So refractions are 2 at this point and also at this point for every color, like this. This refraction here, there's a refraction at this point, then also here. But this one, when it's coming back into air, it is refracted towards the base. This is our base. Okay, now let's see how this finally comes. Okay. Alright, good. Great. So you must make sure that the colors are all 7. You must make sure that the colors are all 7. And if you have to count, this is red, this one here is orange, this is yellow, this is okay, yeah, this is green, this is blue, this is indigo, and this is violet. Those are the respective colors. And realize that from the classroom setting, please, you can simply use a glass prism. Please, you can carry out this experiment and realize that the colors will come out like that. Now let's see where does the curve come from. So that's what you're going to do. In order to get that curve, we are going to put a curved screen. So you put a curved screen and realize that this curved screen here, it is where the colors are going to be casted. The colors are going to be casted onto this curved screen in that format, like that. And realize that that one describes something like the rainbow we have seen in the picture given to us. Okay, now let's continue. So now that has been part A successfully answered. That has been part A successfully answered. Let's see which words come on next. Okay, now we're saying that when white light is incident onto the glass prism, refraction of light occurs. The light is then dispersed, since white light consists of different components which travel at different speeds in the glass prism. Okay, we say by the time they emerge out of the glass prism, they form a curved spectrum on a curved screen. So this is what I've been talking about here. You really see that when light is incident, let's say from here, this first point, when white light, okay, get this laser beam. Okay, we say that when white light is incident onto the glass prism, refraction of light occurs. So refraction is strictly the bending of light when light is traveling from a less optically dense medium to a more optically dense medium. Like, so for example, if light is moving from air and entering into water, we expect refraction there. Why? Air is less dense and water is more dense. Therefore, as light is entering from air into water, we expect refraction to take place. So, and I explain this. Refraction takes place at this point. Explain this. Takes place at this point, because you see that the light ray was coming like this, but it's again a bit unique. It is now becoming straight. It means that it has been refracted. And when it's coming out like this, we expect it to go like that. But what happens? It again bends. So we have got refractions here and a refraction here. Why? It's because this side we are coming from air, and this prism is made of glass, and that glass is more dense compared to air. Okay, there we expect refraction because it's moving from air to glass. Then about this point, at this point here we expect the same, because we are moving from glass to air, and you find that the density air is less dense to glass, so therefore we expect this one to bend towards the normal. Please, all refractions when light is from the prism outside, they should be towards the base, and this is the base. Alright, good. So I think let's now proceed. Okay, to check, we have now the saying the light is then dispersed, since white light consists of different color components which travel at different speeds in glass prism. So now dispersed means spread. This word dispersed means spread or simply split. You can call it split. So the white light is split into different colors, but first we shall say they are split into different 7 colors, which are the Roy Gibiv. We have talked about that. Okay, since white light consists of different components which travel at different speeds in glass prism, yeah, we have explained that. Once it is incident, the refraction, the first refraction spreads them apart. Here realize that what's happening here is now like at this point. Okay, I want us to do this very well. Now realize that here we have only one single ray of light, but when it reaches here, now this one is what we call dispersing, that kind of spreading away in different directions and at different wavelengths, okay, or different angles. We call it dispersing. So you see that they have dispersed. That's what you're meaning by dispersed or splitting in simple, okay, terms. Let's now see the last statement. They say by the time they emerge out of the glass prism, they form a curved spectrum on a curved screen. So now what we do here is, in simple terms, what we do, okay, what we do, we now come and put here a curved screen. Please, it's very easy to get this. A curved screen can be a paper. You make it to form a curve of that kind. It can be a piece of paper like that, form a curve such that you can now view those light rays incident onto there. And now this curved stuff forms something more like a rainbow, and hence it means we have successfully described how the phenomenon of rainbow can be shown in a classroom, okay, setting. Let's now proceed to something else. What do they say in Roman number 2? So Roman number 2 said, remember answering the tasks for these students. Roman number 2 said, explain why the physical rainbow appears curved as shown in the figure 1a, and why is it in position opposite to where the sun is. Let's go and see that. So in simple terms, they are more like asking you, describe how a rainbow is formed. Yeah, explain why the physical rainbow appears curved as shown in the figure 1a, and why is it in the position opposite to the sun. So we go towards opposite to position opposite to this where the sun is, and also why does it appear curved. Let's go and see that. So okay, and as shown as in figure 1a above, let's go and see that figure first of all to remind ourselves a little bit. So that's our figure. So they're asking, why is it like that in that format? Why does it appear curved, and why is it always opposite to where the sun is? Let's go and see that. Okay, now here to begin with, let's see. Okay, let's begin from here. So we have, that's error number 2. Let's see. So to begin with, we shall say that the curved shape of the rainbow is due to the spherical shape of the raindrop. So the curved shape of the rainbow is due to the spherical shape of the raindrop. Now you all know that, before we proceed, you all know that, okay, a water drop may appear like this, depending. So this is more like a sphere, and that's why they are saying that, okay, the shape of the rainbow also takes up the shape of, now that is spherical, and now we shall say that now maybe the rainbow appears on this part here, and that part I'm shading, and you see that part I'm shading it brings out something more like a rainbow. I can see the details. Let's can see the details. Alright, good. So they're telling us that the curved shape of the rainbow is due to the spherical shape of the raindrop. I've explained that the raindrops are spherical. In fact, what we are taking is, you all take it a rainbow, or rather the raindrop, to be circular. However, it is not that, but it is spherical. Okay, white light from the sun is dispersed and refracted by the raindrop into the different colors which emerge. Now, as you are describing this, you should also be remembering the prism you have done. It's more like that. Dispersion of light, and light is also refracted. That's what you must think about. Okay, good. So white light from the sun is dispersed and refracted, is dispersed and refracted. Those are key words, you shouldn't miss them out. By the raindrop into different colors. So yeah, the light is dispersed or split and also refracted to different colors which emerge at different angles. This word, at different angles, to the normal, ranging from 40, by the way, it's meant to be 40 degrees to 42 that is 40 degrees for violet and 42 degrees for red. So these are different angles. Red is refracted at an angle the angle of refraction is 40 degrees, and rather for violet, that's violet, the angle of refraction for violet is 40, and the angle of refraction for red is 42 degrees to the observer. Okay, the curved nature depends on the position of the observer on the Earth's surface. Now that is more theoretical. Let's go and see it from the pictures. You see the way forward. Okay, now here, that's, for example, that's our rainbow, rather our raindrop. So what happens is, we shall say, okay, that's our raindrop. Now we are saying that white light is the ray from the sun is coming and is incident onto one raindrop, and remember, when it is raining, there are millions of them. So those millions of them, what happens to just one raindrop? What happens to that? Then as you have finished that, you imagine millions of raindrops up in the sky. They will bring out what you will call the rainbow. So the light is incident of the raindrop, so it is refracted. You see that here. Let's see. It will be refracted here once this incident here. If you can remember our prism also is like this. Please, this can be explained here. So white light came like this and was refracted. So refraction took place here. We also expect here refraction take place, and this is now this one which is going. Let's now see. Okay, in that direction. So at that level, well, they didn't join well, but it's okay. This is just for demonstration. Okay, in that direction. Now what happens is, you realize that when it is incident at this level, we expect what we call total internal reflection. Total internal reflection means that light is incident into a medium and does not move out. Like, say for example, if I can have this, if light comes like that in that order, and instead of the light moving out, it instead comes back, we call it total internal reflection, because the light has been bounced back. without moving out of the medium. You have not lost any of the light. So let's now see. Okay, so realize that as the light ray comes, just in simple terms, from the sun, comes like that and is refracted, is still in the raindrop. Now what happens is, still in the raindrop, total internal reflection takes place and the light will be driven back like this, and it is refracted back into the air like that. And now that first one there will give us what we call violet light. Remember, we are following the Roy-Gebiv. We are following the Roy-Gebiv. But for us, what we are going to see here, let's see. Well, once you see red and violet, you just know that these other colors are also in between there. So we shall be using R and V. Once you see R and V, just know in between you have the orange, the yellow, the green, the blue, and the indigo. So we have that. Let's proceed. So still the light which is incident here, just like we did for the prism, that one light was incident at this level. Please, I want to use the prism to explain this. Okay, white light was incident here, and they were all spread at different rates. But for to avoid congestion, I've said you shall be using the red and the violet. Just know that in between them we have these other colors. So therefore we can say, so you see that now another light comes, it is dispersed, split. It is one, but it can be split into 7 of them. However, I've said here you shall be using 2, the red and the violet, so that in between them you just know you have these other ones. Let's see. So still, when it comes, it does the same. Total internal reflection takes place here, and it is reflected back, or still inside the raindrop. Okay, then it emerges out. Then, okay, can you now see this? I guess you can all see this. Now you see that we have red and we have violet. That means that in here we have the orange, we have the yellow, we have the green, we have the blue, we have the indigo. In between, please, we have only done this to avoid congestion. That's why we have chosen to use the 2 of them, the red and the violet. Okay, let's proceed. Now what happens is, you realize that in order for an observer who will be viewing this, how will the person be able to see the rainbow? Let's see. So you realize that if, okay, that's virtual image. Now realize that what happens here is that in physics we are imagining what if when this ray came and it went undeviated, this ray went undeviated, then also the rays from okay, now at this point, look well, at this point we have this violet which comes like this. Then also at that point we have an effect of this when you drive this backward, dotted like that. So that in here we are having the violet and the red. So it means that when they go back and they will be appearing, if you put the dotted lines backward, please, this is a diagrammatic way to show it. So when you drive it backward, realize that this will spread in that order and also in that order like that. Now that means that at this level I also expect us to have here the red maybe and the violet there. So that's why now the red and the violet, but remember they occur at different angles. Different angles means that this can come up to that level, another one comes to another level, another one comes like that, another one comes like that. That's what we mean by different angles, whereby red is the largest and this violet is the smallest. Why? Because violet was 40 degrees and the red was 42 degrees like that. And now this one here finally gives us what we call a curve. Now this virtual image here can be viewed by someone on earth. Now we are thinking that now we have our sun this side and our rainbow is occurring this side. So why they occur in opposite directions? Because of the refraction of light rays. In fact, the apparent reflection or the apparent intersection of the rays from the sun and the rays from the total internal reflection inside the raindrop. Now this happens for just one single raindrop, but imagine when there are a million of them. So once the million of them and such kind of process is taking place, you realize that we shall be able to form what we call a rainbow. Let's go and see still. Okay, now this is the picture which we can bring out clearly to you. Okay, I'll use this. So you realize that here we have white light. In fact, we have white light, or rather, you see that we have light. The sun is here, and now the white light comes. This is the 3D version. So light comes and is incident here. Now at this level, I want to explain this. So at this level, this light is split. I think that now we have some red, we have the yellow here, we have the green, we have the indigo, and so on. So this is what is happening. So this diagram we have up here, it summarized the version in 3D is this. So you find that here light has been split. Now what happens is at this level here, total internal reflection takes place. Total internal reflection takes place, and then the rays are reflected back. But when they are reflected, you realize that here we have our violet, and here we have our red. So now for us, we said, as for someone, any eye which can be at this level, any eye, assuming this is our eye, like that, the person is viewing, for him we will be seeing as if the image of this is somewhere up this side, somewhere up the other side. Then 3D version, you chose to put it nearer here, and that can be best explained here. You realize that someone's eyes can be here. So someone's eye can be here. Here, this is the eye viewing, and now this person viewing at this level will be seeing as if this one's here. Now the diagram shows that this and this is near the eye. However, in real life, someone will be seeing it as if it is somewhere very far the other side, and that explains why you see that the sun is this side, the rainbow is this side. So the rays in the opposite direction. Why? It's because the rays, as they come, due to refraction and total internal reflection, makes the sun to be opposite to the rainbow. Now where does the curve come from? It's because the curve comes from, they all have different angles. They all have different angles, like that. So the different angles lead about that curvature, just like the 40 for we say that red and violet. For violet it was 40 degrees, for red it was 42. Now what does it mean? It means that from red you have there orange. It means that orange is very small. Orange is again very small, maybe 41.5 degrees, like that. So the variation in their angles brings about that curvature because they have different angles. Please, you have explained that here. We say that when white light from the sun is dispersed and refracted by the raindrop into different colors. Okay, well, that first point, when the light is being spread, I explain this here. Here, when the light is being dispersed at this level, dispersed means that it was one, but it can make more 3, more 4, more 6 rays, like you're seeing. Okay, or different colors which emerge at different angles to the normal, ranging from 40 degrees for violet to 42 degrees for red. So the difference in the angles brings about that curvature. Then the curved nature depends on the position of the observer on the Earth's surface. Yes, the level of the curvature depends on where you are. Like, so for example, here, if someone is viewing this rainbow here, if someone is viewing, in fact, let's use the 3D. Okay, this is our 3D version. You see that here, at the first instance here, refraction took place. Let's see this. Here, refraction took place to give us those different colors. Now, that refraction here is coming along with that word dispersion. Dispersion. After there, now, at this point, we no longer have refraction, but we have total internal reflection. Total internal reflection means that because that reflection is ever like this, but some light may escape. Okay, but here we want to see total internal reflection. It comes and bounced back without moving out of the medium. So this one here is our raindrop. You can see the real brought out the real shape. Now with you will be seeing as if the rays are coming like this, but someone here will be seeing as if it is very far this side. Now the variation in their angles brings about the curvature. Let's now proceed. Okay, what else did they ask in the activity? So in the activity they asked for, that is part B. Okay, part B, Roman number 1. State the general name of the wave shown in 1B. So general name of the wave shown in 1B, let's go and see. So where is 1B? Oh, now we can see this. Okay, let's see. Now we have the wave is this one here, 1B. It is, okay, let me use the different color. So 1B is this. So what do you see there? Please, by you seeing just this, I can see the radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma. What do you expect there? Now, what you should know is, when it comes to waves, we have two forms of waves. One, we have the mechanical waves, which require material medium for travel. An example of a mechanical wave is sound waves. Then we have electromagnetic waves. Electromagnetic waves do not require material medium for travel. Except, for example, sound requires air to move, but electromagnetic waves will not require a medium to move. An example is when you're using a remote of your TV at home, you realize that you don't need a wire to connect to the TV, but you can command and it will happen as that. So now that's an example of electromagnetic. Electromagnetic does not require a material medium for travel. And when you check on this, the radio waves, when you're listening to your radio station, you don't need a wire from the station up to where your radio is. You may not necessarily need. Now the infrared can be used in heating, especially people who have the chicken farm who rear chicks. They sometimes use infrared to provide some heat in there. Okay, even the X-rays, you realize that when you go into for a scan, they will use the X-rays into your body so they can view the body organs inside, and that does not involve cutting or connecting any wire onto your body. So they are finally electromagnetic. Why electromagnetic? Is because they do not require material medium. We said there are two types of waves. Mechanical requires a medium for travel. Electromagnetic, with it can move in a vacuum. Let's go and see that. So let's go and answer. So we have known that is now electromagnetic. Why? They don't require material medium to travel. An example is a remote, the one you use at home. Let's go straight to that. Right. So let's straight away go to that. Okay, well, still about the other one. We see that the rainbow appears on the opposite side because of total internal reflection. I explained that. Since there is okay, so finally we have that. We are saying that the rainbow appears on the opposite side because of total internal reflection. Since there is reflection, an image is formed on the opposite side of the light. So here what we're meaning is, now one would still ask, why do we form the rainbow? You imagine if you have a plane mirror like this. This is our plane mirror. Of course we know that reflections take place here. So if you have an object here like this, the image will be formed this side. So this here is our object, and this one is our image. So you are saying that the once where reflection takes place means that the object must be on the opposite side to the image, and that explains why the rainbow. Now this will be more like our sun, and this now will be our rainbow, like that. Okay, so that's what you are meaning. So with reflection, they must all be formed on the opposite sides. That has been successfully explained. Okay, good. Now let's proceed still to our part B. Now part B, Roman number 1, they were asking us which type of waveform is that was been here. Part B, Roman number 1. State the general name of the waves shown in the figure. We have agreed they are electromagnetic waves. Let's go there and see. Okay. Okay, so we have agreed that the electromagnetic waves or electromagnetic spectrum. Why electromagnetic? Is because it does not require material medium for travel. Okay, let's now go to Roman number 2. What were they saying? Roman number 2. Roman number 2. Okay, Roman number 2 is saying explain. Okay, let's see this. Say that explain the effect of the two radiations at the extreme ends of the figure on the photographic plate. Now they want to see the effect of the two radiations at the extreme ends of the figure on a photographic plate. Now a photographic plate, I will explain this. A photographic plate is more like, if you have ever gone for a scan, there is that paper which is sort of like polythene, kind of like blue, whereby if someone maybe has got a fracture of the bone, that's what we call a photographic plate in simple terms. So let's go and see. But now I've said that the two radiations at the extreme ends, let's go and see from the picture which radiations are those. Okay, from the picture you see that. Okay, from the picture you see that. Now we have this. So we have this radiation at the extreme end. Okay, if I'm not mistaken, we have the radio waves and we have the gamma rays. Those are the ones at the extreme ends. This is one end and this is the other end. So they want us to give the effects of radio waves and the gamma rays, their effects on the photographic plate. I've explained what a photographic plate is. Okay, let's go and see Roman number 2. So now the two radiations at the extreme ends are radio waves and gamma rays. We have really looked into that. Let's now go and see their effects. So you realize that when it comes to the effect, you see that the radio waves, these ones are got from the radio stations, and really, if you really so think about it, can those frequencies got from the radios cause any effect on that paper, that scan paper I've explained? No, but the gamma rays can. Why? These gamma rays can even used in some X-rays, or rather the scan machines. These gamma rays can be used. So you find that the gamma rays have got an effect on a photographic plate and the radio waves do not have an effect on the photographic plate. Let's see. So I say that gamma rays darken photographic plates because they are highly penetrative due to their high frequencies, a lot of energy and short wavelength. Yes, with gamma rays, with them they have got an effect. In fact, what you see on the after scanning that paper they bring out, that one is sort of like blue polythene, which shows the inside parts. Especially if they are carrying out a scan about TB, then it will show that those parts of the ribs. If it is a broken bone, then it will show that part, the inside parts. What brings that? In fact, what you see, the picture of the bone on that paper, it means that the rays pass through and bring an effect on the photographic plate. Okay, now you see that the gamma rays have got an effect on there, and what do? They darken the photographic plate because they are highly penetrative, meaning that they can pass through a hard surface including a bone. Okay, in simple terms. So let's go and see how about the radio waves. So with the radio waves, shall I say, radio waves do not affect photographic plates because they carry low energy and less penetrative. Yes, with radio waves do not carry or cannot affect the photographic plate. In fact, an example of radio waves, those are the ones you receive from the FM radios. they don't really have an effect on a photographic plate. As simple as that. So now let's proceed. Let's see. Okay, let's proceed still. So Roman number 3, let's go and see Roman number 3 from the question. So Roman number 3 says, so you have answered this, the effect of the two radiations at the extreme ends. You have seen that the gamma rays have got an effect on the photographic plate, while the radio waves do not have the effect. Then Roman number 3, explain the usefulness of visible radiation. Now, a visible radiation, have it here. A visible radiation, have it here. This one here, the visible radiation. Okay, let's go and see the use of that visible radiation. Let's go and see the uses. Okay, let's see. Now, first of all, with the visible radiations, they enable us to see. Yes, from the word visible itself, it means that you can be able to view. In simple terms, you can say enables us to see. Another one, plants use visible light to carry out photosynthesis. Yes, so visible light can be got from the sun. In fact, can be got from the sun like that. So next, it is used for artificial lighting. Yes, you realize that you can use the visible rays for lighting. Like say for example, the light from the small sources of light, artificial ones, like light from a bulb, you can take it as that. So used in motion sensors for security alarms. So the visible light is used in motion sensors for security alarms, whereby if someone tends to pass in a certain region which is prohibited, the sensors will detect the motion, and in fact the visible spectrum will detect something, and then later on they will make the alarms. So used in electric heaters, then also used in infrared cameras for surveillance. So a lot. However, here we gave generally the uses of electromagnetic waves. You may discard this. This one is used for infrared. You may discard this. It is also for infrared. So for as far as the visible spectrum is concerned, you can take this, photosynthesis and artificial lighting, like that. These other ones here may work for what you call infrared radiations. Okay, let's move on. Alright, so let's proceed. Let us proceed. Okay, let's now move to the next part. The next part, we are meant to answer part C, Roman number 1. Let's go and see what part C now, Roman number 1 is saying. Part C, Roman number 1. Part C, Roman number 1 is saying, use the figure 1C to determine the amplitude of sound waves. Amplitude of the sound waves. So let's go in figure 1C and we see how we can get the amplitude of the sound waves. Let's go and see from figure 1. Amplitude of the sound waves. So figure 1C, we have it here. Now where do we get the amplitude? Now the amplitude is the maximum displacement above the mean position. So you realize that with this, okay, the amplitude, now like what you call the mean position is this. If you can see where this, okay, let me use some different ink. Okay, if you can see this line, the wave is going, but you can see this line here. I'll put a red line there for you to see. Okay, well, I may go off, okay, a little bit, move this. Okay, in fact, in simple terms, what I'm meaning is this line here. If you can see this line here, Okay, now what you call the amplitude is the distance from that line up to where the wave ends up this side. That's what you call the amplitude. Now have they given us that distance anyway, and it should always be in meters. Let's see. And now the symbol for amplitude is small a, so we shall say small a is equal to, do you have it? Let me see. Distance from here upwards. Okay, like we are now. I think from here, you see that from here we come to -10, and from here we come to 10. So that the distance from here up to this one up is what we call the amplitude, and that will be, shall put now our amplitude is 10. But then the units here have been given to us as centimeters, so I will say equal to 10 centimeters. Now here we just need to convert this into meters, whereby you say that A is the same as our 10 divided by 100. Okay, of course you all know that 1 meter is equal to 100 centimeters. As simple as that. So when you divide, you get that A is equal to 0.1, and that is meters. Let's go and see that. Okay, so amplitude is equal to 10 centimeters, and we have it as 0.1 meters. I've already explained that. Let's now go to part C, Roman number 2. Let's go and see what they want. Okay, part C, Roman number 2, we have this. We have, okay, they want us to find the frequency of the sound waves. So frequency of the sound waves, remember we have got our amplitude. So frequency of the sound waves will be got from, now we all know that in waves we have that velocity is equal to lambda times f, whereby f is the frequency. Now the lambda, this lambda here, is what we call a wavelength. Is what we call a wavelength. Is what we call a wavelength. So let's see. Okay, they want us to get f. Do you have the velocity? Yes, it has been given to us in the question. We have it here. So they have given us the velocity of sound in air. The velocity of sound in air is this. So the velocity, we have it. So let's go back and see. So the velocity, we have it. Now what we need is lambda. Lambda is same as wavelength. Let's go and see how we can find the wavelength. So now what we call the wavelength here, I'll use the blue ink. So what we call the wavelength is, now since with the amplitude it was from here up, that was amplitude. Now wavelength means from one cycle to up to that point where your complete cycle is. In fact, what we call a wavelength is starting from here back and back. That's what we call a wavelength. Here is what we call a wavelength. That's what we call a wavelength. So let's see what is our wavelength here. So realize that here we have this, there is a wavelength there, another wavelength, because we are going like this, back and back, that's a wavelength. Again, to and fro, that's a wavelength. Again, to and fro, that's a wavelength. Let's see now what's going to be our wavelength. Now realize that which distance are we having here generally. Okay, so still you realize that now how shall we get the wavelength? Remember I told you that the wavelength means, in fact let me use yellow. Okay, wavelength means, like say for example from here up to here, that's a wavelength. Then start from there, from here up to there, that's a wavelength. Why? It's because, okay, let me use a different ink so that you can see. Why am I calling that a wavelength? Is because when you see that, you realize that when you go up, I'll just be drawing against this, up and back down like that, that is a wavelength. Then from here and back down like that, that is a wavelength. Okay, so how many are they? So let's go and see. Still use your light. Okay, now from here up to here is also another wavelength, and from here up to here is also another wavelength, and they must always be equal. For any wave, wavelength is always the same, meaning the distance meaning that the distance from here up to here must be the same as the distance from here up to there, must be the same as the distance from here up to there, must be the same, okay, there must be equal to the distance from here up to there. So wavelength is always the same. Now what you're going to do to get this wavelength, let's edit. We have here negative 20, then lastly we have here 20. Now I want to see from negative 20 which value they put here, and it should be that value, a common value we use, should give us the 20. Let's start with 5. When subtract here 5, it will be negative 15, negative 10, negative 5, negative, actually, in fact I shall have a 0, it can't come out. So I'll try to use 5, like what I'm meaning, at this level, if I put 20, okay, get different ink. Like here, I will come and put here a 5. I will, okay, yeah, negative, in fact, when subtract here a 5 to be negative 15, like that. So I shall have negative 10. You're subtracting a 5 continuously, then it will be negative 5. Subtract a 5 again. In fact, we add 5, not subtracting, we add 5, so plus 5, negative 15, plus 5, negative 10, plus 5, negative 5, plus 5, we have a 0. Now I think, is the 0 rhyming with the 20? No. So we come back and say, no, this is not working out. We remove it. Okay. So it is not working out. So 5 has failed. Let's try using 10. So this time around I want to use 10. So if I'm to use 10, from 0 to this, plus 10 will give us negative 10. You can see that. Plus 10. Okay, remember I told that from here up to here also. So okay, from here up to there. So plus 10, it will give us 0. 0 plus 10 will give us a 10. Then 10 plus 10 will give us a 20. Now do you see that? So you realize that the difference between this level here, this minus this, will give you, there is a difference of 10 there, difference of 10, then there is also a difference of 10 here, then there is also a difference of 10 here, then there is also a difference of 10 here. 20 difference is coming from this minus that gives you 10, this minus this gives you 10, that is a 0, and this minus this gives you 10. So it means that our wavelength, in fact our wavelength, which they call lambda, will also be equal to 10 centimeters as indicated. So let's can see. Okay, let's can see. So the wavelength is 10 centimeters, but when you convert to meters you get 0.1. Now let's use the formula. So from V is equal to lambda F, you realize that we are substituting now in our formula. So it means that our V, this is our velocity of sound in air, this is our lambda. We are now looking for the F. Let's go there and see. So when you substitute, you realize that making F the subject, we shall have that 0 point, rather we shall have, okay, so we shall have 330, divided by 0.1. I've made F the subject. You'll give us now 330, rather 3,300 Hz, and that was the frequency of the waveform. Alright, good. Let's now go to another question. Okay, so we have now stepped in for Uneb Uce Physics item 2. I said this paper was done last year in October, the first paper of the new curriculum, physics. Let's see. So they're saying a patient has been, oh sorry, there's some typing error here. So a patient has been taken by relatives to a hospital complaining of severe pain in the neck. A doctor has admitted the patient in an isolated room and decided to examine the functioning of the thyroid gland. Okay, in the process of examination, a radioactive isotope, this is where our answers will come from. A radioactive isotope has been injected into a patient to be used to diagnose means more like to see or to find out the thyroid disorder. In fact, what is wrong with the thyroid. Okay, good. They're saying the activity of radioactive isotope from thyroid gland is detected and recorded as follow. So now the activity, like say for example, what we call radioactive substance, it must give counts per minute. In fact, it gives counts per minute, because when you are in there, that room, you have a calculated time. Why? With the radioactive isotopes have got a big effect on human beings, and you can end up dying, or if not, you can end up contracting cancer. So therefore, they must calculate the time which you must be there. So time in hours of a radioactive isotope. Okay, good. Let's see. Now it is as given in this table. Let's proceed with our question. So they're saying, continue. Whenever the relatives of the patient, get this letter B. So they're saying, whenever the relatives of the patient want to check on him in the isolated room, the doctor tells them to wait for the right time. In fact, right time, what does it mean? When the activity is equal to the background count rate of 40. Now, what I mean here is, in simple terms, like what you call the right time is every, like these count rates are measured by the radiation detectors. Like you can think about a gauge molar, a GM tube can be used to measure, and different radiation detectors have different background count rate. Now, what do we, in simple terms, what do we mean by the background count rate? In fact, that's the time when a background count rate means that when radiations are off, how does the monitor read? Now when radiations are off, this machine shows 40. The count rate is 40, meaning that it gives 40 counts per second. 40 counts can be like, you can take your heartbeat. Like, so for example, your normal heartbeat pumps at 72. That is normal. When it goes to around 80, we say that someone is sick. Now, for this machine to work well, to be safe, in fact, for it, the time when it is not dangerous, it should be that we call it now a background count rate. That's when it is safe. Now, like your background heartbeat is now 72. That is normal. So it means that this background count rate of 40, that's when it is normal and there is no radiation. In fact, background count rate is just a radiation measuring the sun radiation, the heat around, without a radioactive isotope. That means that that is not dangerous. Okay. The doctor has also informed the relatives that if the right time for them to check on the patient comes, they must observe precautions in the isolated room. Okay. The relatives have demanded to know the period they should wait before they can check on their patient, but no one answers them. Now, about the period when they should check is here. Let me go and explain. So look, when you see that here we have the activity counts per second. Now I think these people shouldn't go in there when the background count rate is not 40. I've explained what background count rate is. Now here it is dangerous when it is 480 counts per second, dangerous. 280 counts per second is dangerous. 178 counts per second is dangerous. 100 is also dangerous. 60 is also dangerous. Now you see that as we go to 35, we have gone past the 40. Now it means that 40 is safe. In fact, the word background count rate means it is now safe. No radiation is there at all. So they should only go there when it is 40 counts per second. These other ones are deadly and dangerous. Okay. Okay, you have heard the doctor talking to the relatives and they have contacted you to address their concerns. Tasks part A, number 1. Use the data in table 1 to determine how long the relatives should wait before they are allowed to check on their patient. Now, how long should they wait? You can all see that from here. I think that for 480 counts, 0 hours token, 280 10 hours, 170 20 hours, 100 30 hours, 60 40 hours. Now when should they check? In fact, our advice is these people should check when the background count rate, when the background count rate is what? Is 40. But you don't have 40 in this table. The 40 would give us the time. That 40 has been 60 and 35, of which here, okay, 60 and 30, so it means that 40 is in here, so we don't know 40 has which hours. It means that our hours should be between 40 to 50 hours. However, since we are scientists, let's go via the graph. We plot the graph and the graph will tell us what next. But what you should know, they should go and check when the count rate is 40. The time at count rate 40 will be the time for when they should go and check, or how long they should take to go there and check. Okay, now with that we shall need our graph. We shall need our graph and the title is given there. Please, a title is highly called before. Let's go through our graph. We plot the points. So we're beginning with the axes. Okay, we are proceeding, labeling the axes, demarcating them. Please, this all awards you some marks. This all awards you some marks. Okay. Make sure you use a good scale, please. Okay, great. So after getting that good scale of hours, let's go about the plotting. Let's go about the plotting. So we plot. You find that in the table we had the 480 counts per second were at 0. 480 counts per second. In fact, these are our counts per second. This is where we have our counts per second. Then this is where we have our time. You don't know. Okay, let's now move on. So realize that at 480 we have 0. In fact, let's plot all the points. Okay, so realize that at this point when it is 480 we plotted it at 0. Then next was 280 counts, then we plotted at 10. So at 10 we plot 280 counts. In hours, at 20 hours we plot 170. Please, you can look out for your scale. That is our 170. Then at 30 hours we put it at 100 counts per second. Then at 40 hours we put it at 60 counts per second, and finally at 50 hours we put it at 35. Then there we must draw there a line. So, and now our line should move like this, going through these points. Like that. That's how our line must appear. Let's see. Let's see how this line will come about. So that's our line. We are drawing it there through the points. Make sure it passes through the points. Make sure it passes through the points. Make sure it passes through the points. Okay, good. Now what they wanted here was, in fact I'll try to comment on this. What they wanted here was, they want to know when should they check. And then we have said Okay, please, I said this down here I have time, this is time, and this I have the count rate per second. The count rates are this side, that is time. So they wanted to know how long will they take to check on their patient. But they've said that you only go and check on a patient when you have 40 counts per second. Or in simple terms, this is the background. A background count rate. Background means that they are just the machine is only detecting radiations which are near, not isotopes, not reductive isotopes, but just radiations which can be if there is water around, if there is if there is some sun or heat inside the room. That's what the count should give, 40, and 40 is safe. So now it means that in order we want to know when does the count rate of 40 come, because here we started with 480 downwards. So when shall we get the count rate of 40? So what you do, you come on this scale and look out for where 40 is. Come on this scale and look out for where 40 is. Have your 50, then where we see the 40 will be around here, maybe draw a line there where the line cuts meets the graph downwards. That will give you the time when they should check on the patient. Why that time? Is because 40 counts per second is one which is safe. So you come and look out for the 40 counts. You come and look out for the 40 counts here. Now once you see the 40 counts from this, draw that line to join the curve, then where it meets the curve downward. That's really the time which is required. Let's can see that. Okay, you see that you have that dotted line, that our 40 is somewhere here. Our 40 is somewhere here. Then I have 40 here, so dotted line to the curve. Then also proceed downward, so that our answer is going to be here. It means that our answer is this in terms of hours. That will be our answer. Let's see. And when you read very well, you see that you get 48. But however, remember down here it was in time, so it will be 4080 hours. So this was in time. This will be 4080 hours. So therefore, that it means that these people, the relative, should wait for 48 hours in order to come up with, or in order to be able to go and check on their patient. Let's go and see that. Yes, so sorry, the axes have come on later, but if I remove this, you can now see I have our time here. Okay, here's the laser. So we have our time here, and another, and the vertical axis also has been labeled like this. Okay, so that's what we have. Let's proceed. So now part Roman number 1, they asked how long should they wait, and they want us to let them. So therefore they should wait for 48 hours. So from the graph they should wait for 48 hours. We have indeed seen that. So you realize that now we go to Roman number 2. Roman number 2, still about that question. They said Roman number 2, part Roman number 2, they say explain the reason, explain the relative why they need to wait for that time before they enter the isolated room. Explain the relative why they need to wait for that time before they enter the isolated room. So they want us to explain the relatives why they need to enter. They need to wait for that time. Now, okay, well, the problem here is this can happen to anyone. So like you go in hospital and you are very eager to see, then they really wait for 48 hours, and which you say that 48 hours, this is equivalent to 2 good days. That's a bit hectic. So therefore now they want you to give the reason. You explain to these parents here, or to these relatives, why do you think they should wait for those 48 hours? Can't they just enter? After all, they have their relative in there. Let's see. Now the reasoning is it's very dangerous. Radioactive isotopes are very, very deadly. So the starting from 60 counts and above, 60, 70, 80, 400 and so on, that is very dangerous and not advisable to go there. The only safe count rate is 40 as per the machine used here. So let's see the reason. So before that time, we want to reason out. And they say that, okay, say that before that time, the radiations from the radioactive material are highly dangerous and may cause harm to humans. Yes, that's very true. Before that that time, then that time is corresponding to the 40 count rates per second. So after that time, the material will not cause any danger to their lives, since the levels of the radiations would have been below the background count rate radiation. Now below the background count rate radiation is that it's 40, but below can be 38, 35. That is now safe. 40 and below, very, very safe. In fact, if they are to use like a gauge muller, with the gauge muller itself, it has 24 counts per second. That's the safe way. And I see that the 24 actually it has 24 counts per second. I see that 24 is below 40, saying that for any machine which uses radioactive isotopes, the safe point or count rate must be 40 counts per second, which we call the background. Okay, right, let's now proceed. Let's now go to part B, Roman number 2. Now part B, Roman number 2 here said, part B, Roman number 2 here said, part B, Roman number, oh, that's part B, Roman number 1, sorry. They said, state the precautions the relatives have to observe inside the isolated room. So precautions are more like rules. Which rules should they really follow when they are inside the room? You all know this. These are dangerous rays, and therefore it means that 1, they should not eat when there. 2, if they have fresh wounds, they must go when the wounds are covered. Okay, let's talk about that. So they should not eat or drink while inside the room. That's not true. Should put on personal protective equipment like gloves, lead jackets. By the way, this one here is lead jackets, very sensitive. Lead jackets, boots, protective gears in simple terms. Let's go and see. Cover all the wounds. Cover all the wounds with thick wool, because the wounds may absorb those radiations and you may end up contracting cancer. Then also avoid direct contact with the patient. Okay, if a patient has been exposed to those radiations, please, you shouldn't make any mistake of moving near that person or even touching him, because you never know, he may be still having the radiations still in there. So this time of exposure while in the room, so this is very practical. You realize that when you go for an X-ray in a hospital, you find the doctor doesn't keep himself inside that room. He is always out. It means that these radiations can't be seen by your naked eyes, but they will be killing you unknowingly. Let's now proceed. Okay, in our proceeding, we have part B, Roman number 2. The other was Roman number 1. And here they said, in part B, Roman number 2, please you can cross-check and refer back to the question. They said, explain why relatives should observe precautions when inside the isolated room. Now, the precautions were not eating well inside the room, covering the wounds, then also reducing time of exposure. Now, why would they really bother themselves with that? They want to give a reason. Why are they being bothered by all that? So the first one shall say, it's because the radiations can cause. Now here we give effects. We say that the radiations can cause cancer, so they shouldn't go there. They can cause sterility or infertility, especially in men. Then you can cause skin irritation or burn. You can receive what we call a skin burn, though this one is a bit rare to. Skin burn especially works when it comes to the whites, but the blacks I think we're a bit strong when it comes to that, but the whites are prone to that effect of skin burn. So genetic mutations. Okay, now with genetic mutation, this can be seen from the towns in Japan, the Hiroshima and the Nagasaki. You realize that such radioactive isotopes go about spreading your genetic mutation, and this may lead to you can produce a child when this child doesn't have one eye, has only one leg, or even has 3 legs. That's what we call a genetic mutation. Okay, the genes will be mutated or destroyed. That's what we call a genetic mutation. Like we are in Africa, we have never experienced that. It is only in those so-called developed countries. Then also it can bring about blindness. We are looking at explain why relatives should observe the precautions when inside a certain room. Yes, they should observe the precautions or the rules when inside the room to avoid contracting cancer, to avoid becoming infertile, to avoid skin irritations, to avoid genetic mutations, to also avoid becoming blind. As simple as that. And now that makes the end of that item 2. We now kickstart to item 3. Okay, let's go there and see what is meant to be done. So now in item 3, we are going to see a lot, especially about our country. So they're saying some regions in Uganda, let me get a laser pen here. So they're saying some regions in Uganda are affected by the changes in seasons. That sometimes may lead to famine. Accordingly, the people in Uganda have been demanding for solutions from the government to ensure that famine does not occur anymore. Good. In November 2022, the government launched a satellite into lower Earth orbit through the support of the International Space Station, ISS. A number of people criticized the move by the government to launch the satellite into the space, claiming that the satellite will not solve the problem of famine in Uganda. Okay, now to talk about this, you realize that this, for those who are a bit, if I'm not mistaken, for those of you who are a bit keen, with the details, you realize that I was still saying that, please, for those of you who are very keen about the news, we got to know that in November, that was 7th November in 2022, that day does not really mean anything in our great. So let's now go through the task part A. As a student of physics, help the public to understand the occurrence of seasons. We shall need to underline this. So we should now explain the occurrence of seasons. But make the people understand and appreciate reasons why the government of Uganda took the move. Now this move is all about setting up what we call a satellite. Why did the government bring up the move? But however, just to explain why they put this satellite, satellites are very important in very many ways. However, the one they launched in November, it was to predict, in fact, for weather forecast, so that they can know more about the weather. When is it going to rain? When are we going to have a longer drought season? Like that. That's the aim. However, still, the news about the satellite is that when they put it in the space, in fact, it is NASA which is concerned about putting up those satellites there. NASA is a body located in USA, but it didn't really work out the way Uganda expected. Some things were a bit lacking, and it was launched, but it had not started its work very well. That's why I say that weather prediction in Uganda is not that okay. So NASA, which is the National Aeronautics Space Administration, that's how NASA in full is, and it is located in Washington DC. However, that history may not really carry sense, but maybe someone needs to know about it. So let's proceed and see how we shall answer. So we want to help them know the occurrence of seasons. How do seasons occur? Now when it comes to seasons, we have very many seasons. We have winter, autumn, we have spring, we have summer, like that. Though in Africa we call them something different. Let's go and see how the seasons occur. To start with, part A. So you're answering about the occurrence of seasons. Okay, good. Now they're saying that seasons occur due to tilt of the earth with respect to the orbit and the revolution around the sun that occurs throughout the year. So what I mean here is, in simple terms, I'll get some pen here to use. So now you just imagine this is our earth, like that. Now the axis of rotation, I'll use a different ink. The axis of rotation is here. That is our axis of, because the earth rotates. That's now our axis of rotation. This one is axis of rotation. Okay, now what happens is, this earth is rotating. Let's also have here our what? I'll use yellow. So this is now our what? Our sun. So as sun rays come onto this part of the earth, you find that when this earth is rotated, you find that the face which is facing the earth here like this will experience the sunlight. Allow me shade like that. This one will experience the sunlight. And now this part, the other side, allow me use blue for that. So this part is not experiencing the sunlight here like this. Okay, now this one is not receiving, this one is receiving. So the part which is not receiving, this one is receiving, this side is not receiving. Now the one which is receiving, the sun, will now be in summer. The SP may not carry sense here because I'm using the ink pen. So we call it summer, which in Africa we call it a dry season. Then up this side where the sun is not reaching, because of course you know the earth is circular. You just imagine a ball, then you get a ball and you flash light from one side. You see that this side will be lighting, you will see some light, but the other side will be dark. So now this side which is dark here will now be in what we call winter. It can be winter, or sometimes they call this autumn. Autumn is also a season. Now winter and autumn means that in there we are not having enough sunlight. Where sunlight is summer, whereas we have no sunlight is winter or autumn, like that. So now, but remember about the earth, we curve this still. Now this being our axis of rotation, this axis of rotation of course is what we call hemispheres. Now this upper part we call it the northern hemisphere, and the downer part we call it the southern hemisphere, like that. Now we also have that versus the equator. Remember the equator divides the earth into two equal parts, like that. So when the sun is around this point here, of course when the earth is rotating, the earth rotates. If the earth rotates in a way that, okay, let me show this. The earth rotates whereby if our equator now will be, remember the equator divides the earth into two equal parts. The axis of rotation remains the constant. It is there. That's the axis of rotation. And now here, this one here is our equator. Now if the sun is here and the sun is now lighting from this level here, it means that we shall experience two things. One, this side is receiving the sunlight, this side is not receiving. So here we shall be in here we shall be in summer, and the other side we shall be in winter. But where the sun is overhead the equator, when the sun is at this level here, now we receive what we call an equinox. Now equinox, for you who know the prefix, the word equi means equal. So equinox means that in the whole world we shall experience equal number of we shall have this equal days and nights, meaning that it is 12 hours in a day, the whole world will have 12 hours in a day. then 12 hours in the night. That's what we call an equinox. And in fact, that's just a brief intro on what we're going to go through. Let's go there and see. So I've already explained that. So the part of the hemisphere of the earth close to the sun, I've explained that, receives more sunlight energy and experiences a longer daytime. That is summer or dry season. I've explained. Let's see. The other parts of the hemisphere that face away receive less sunlight and experience a shorter daytime, hence a wet season or winter season. I've explained all that. You can rewind the video. Okay, good. Let's proceed. So more details. Now, during the times when the daytime and night times are equal, that's the equinox I explained. When the sun is overhead the equator, spring and autumn are experienced. So now, when the sun is overhead the equator, like I will explain this once more. Okay, this is our Earth, and this is axis of rotation. So our equator, allow me to use red and dotted. So our equator is that. Dotted is our equator, like that. So if the sun happens, I'll use yellow. If the sun happens to be here at this level and is flashing light, you know that the axis of the equator is pointing in the same direction where the sun is. It means that this part which is receiving light will experience will experience this, what we call spring. That now be spring. That season called spring. Now this part which is not receiving sunlight will experience a season which we call autumn season. Autumn is more like the wet season, or rainy season. That is what we call autumn. I experienced. So take note, spring and autumn are experienced when the sun is overhead the equator, that direction. But these other ones, the wet season, the other ones happen like this. I just want to read this for some people. So we have that, and this is our axis of rotation. That one doesn't change, please, and the earth rotates in that order. It can move in that order like this. The earth rotates, okay? The earth is in one position, it rotates about a certain orbit, the axis of rotation. So now we have this is our axis of rotation. Now allow me put our equator, use red ink still. So now here our equator is like this, still dividing the earth into two, because the earth has been rotating. Here when the equator is like this, it means that earth has rotated until when the equator is overhead the sun, or the sun is overhead the equator. Now here when the equator is like this up, so it means that the sun, our sun is here and bringing light. Now the sun has nothing to do with the equator. Now when sun has nothing to do with the equator, it's not overhead the equator, the part which is receiving becomes the winter season or wet season. The part which is receiving the sunlight becomes the summer or dry season. The part which is not receiving becomes the wet season. That's the simple explanation I can give. So let's go and see what next. Okay, proceeding. Okay, good. Now let's see this in picture, maybe for some people to understand better. Okay, this is what I was trying to mean. Like, if you can see now, like at this level, this is now our axis. This is now our axis, and the earth is rotating in this order. In fact, let me get a laser beam. So the earth is rotating in this order like this. That's how it is rotating. Our earth is rotating like that. Now we have here our sun. Now here, someone may think that here the earth has moved, but we are showing rotations. The earth is in one position, but here at this level it means that it has rotated. That's what it means. Now like here, when it is in this level, now here that is 21st March and 23rd December. We always experience equal days and nights. Why? It's because the equinox is taking place. Really, what equi means is equal. So mean that at that level equinox is taking. Okay, so let's proceed. Now you realize that here at this point the equinox here at this level and this level, when the sun is overhead the equator, when the sun is, remember the equator divides the earth into two equal parts. Now at this level it means that when the earth rotates, I've already explained this, but this picture may confuse some people, but I think the explanation I gave at first brings out clearly. Now you see that at this level, when the earth moves and rotates up this level like this here, we shall experience what we call an equinox. But from there, when the earth now okay, you can now see from here. So I think this part is lighting, this part is dark. So here it will be a daytime, here it will be night. The part receiving the light, it will be day. The other part is not receiving light will become what? It will be a night, like that. Now what does it mean? It means that this one is receiving the sunlight. Of course, this is sunlight directing here, and you see that it is lighting this area. That area there will experience summer or dry season. Then this other part will experience what we call the wet season or winter. Now from there, of course, this is summer. Now this spring is for this one, this summer is for this one, like that. This autumn is for this one, like that. Then the winter is for this guy. So let's come now. I want to explain this level and this level. So at this level, it means that as the earth rotates, remember this part didn't have, so as the earth rotates further, the other side, you know that here it is showing the map of Africa in some other way, but here it is also showing the other part, the remaining part, which was dark. Here this part, now I'll name this one part A. In fact, let me erase off this. Okay, allow me name this as A and this as B. So the rotation from here up to here makes this is now your B and this is now your A, like that. No, okay, okay, well, let's see this. So this will be your A and this will be your B. Now when this happens, this now becomes your A and this becomes your B. I think that they all share. Here A was dark, but the rotation made A to come also light. So this one, which was originally in winter season, when it rotates up this level, they will now be in a dry season at that level. Then also in dry season here will now be in winter or wet season, and that's most especially in some European countries. Africa, we don't necessarily have winter apart from South Africa. Okay, good. Now why don't we experience winter is because with us we are near the equator. In fact, in simple terms, that's what the explanation you can give. Now here, where this one is taking place, means that the equator, the sun is overhead. Allow me put that as the equator, like that. Now here, when the sun is overhead the equator, we experience what we call an equinox. And this always happens on 21st March and 23rd September. But that may not really bring any sense. They will not ask you for those dates. So sun overhead the equator, what do you expect? The spring season and the autumn. Spring is where the, like here, the way it is here, this part is receiving sunlight, it will be in spring. The other part which is not receiving will be in autumn season, like that. That's what I mean in simple terms. I hope that makes some sense. Let's move to another number. Okay, now let's go now to part B. So part B, what do they want? Now with part B, they were asking you, okay, let's go and see part B. So part B, they were asking, make the people understand and appreciate reasons why the government of Uganda took the move. Now the move was about installing the satellite into the space. Now installing the satellite in the space, it was a weather satellite which could foretell when are we going to have the rain, when are we not going to have the rain, such that the farmers can be on board and wait. In fact, it gives a lot of details concerning weather. So they're asking, make the people understand and appreciate the reason why the government of Uganda took the move. So why did the government of Uganda take the move of putting up a satellite in the air? They wanted to make people understand. Let's go about that. So the satellite. So first of all, we must tell these people that the satellite launched was a weather satellite. And how was the weather important? It helps us, of course, in our agriculture. Now, what does a weather satellite contain? Let's know. So now, with a weather satellite, it has instruments such as cameras, pyrometers, barometers, and many others for collecting data. Now, for those who don't know, this one here, a pyrometer, is a specific thermometer which measures heat, especially too much heat. You know that the thermometers in hospitals, when you put them to a temperature of around 1,000 degrees, they will just melt. But a pyrometer can measure even up to around 1,000 degrees Celsius. Okay, so a pyrometer is a thermometer used to measure temperatures. So I see this satellite goes with a camera, a pyrometer which can measure temperatures, a barometer which can measure the humidity, and many others. In fact, it comes along with a lot which collect data. And when you talk about weather, of course, just know somewhere this satellite to be able to measure the rain, the amount of rain received in a certain area. However, though in your geography you go to know that you can as well use a rain gauge, but that is some local way satellite makes it better. So these people of Uganda should really know that the satellite is very, very, very important to them. Let's still see. So now we must tell them how this satellite works. And now they should know that after the data is collected, it is sent to the ground station. In fact, how a satellite works is this. After data is collected, it is sent to the ground station in form of radio waves. We learned about radio waves, where it is processed, analyzed by meteorologists who make accurate predictions of weather in a nearby future. Now what happens here, maybe I'll make a drawing. So if this is our Earth, this the ground, and imagine this is our space, and in that space there we happen to put there our satellite. Our satellite is there in the space. That's our satellite. Now what happens is this satellite here, like it has these pyrometers here, it will be able to measure the temperatures around a certain place which they are forecasting. Say for example, they want to measure temperatures in Kampala, so they can tell the people in Kampala whether they will have rain or not. That satellite will focus onto Kampala. Then the satellite with it, what it will do, it will collect data from that Kampala, that venue they have focused onto. Then later, after collecting it, it will process it. It will collect that data and it will send it to the ground. So after getting the data, it will send to the ground. Now this ground here, it will just come like that. Now the radio waves are more like, for you, just imagine like that FM radio you listen to. That FM radio you listen to, and for you at home, at your home, you are a receiver at your home. Now how do those waves reach you? So now you just imagine that this FM radio, where it is located, is our satellite, and now it is sending you to interpret. That's what happens. So it sends the data collected to this. Of course, this is a heavy station whereby it is installed with the computers which can read data from the satellite, and with that we'll be able to tell whether they will receive some rain in Kampala or it will be a bit sunny, such that they can let the people know about the weather in the nearby future. So in simple terms, that's what these people should know. One, that they launched a satellite. Its use is it is a weather satellite which will help in predicting the weather. So now with meteorologists, these are people who know much about the weather. So now these meteorologists, these are human beings who are located in the ground station you have talked about. A ground station can be like a big house whereby people are gathered with computers. Their work is to only analyze what the satellite is saying, and now in the nearby future they come. Like of recent, please, in the early Feb there we had too much heat. And somewhere they came out and said in February we had too much heat. Then they come out and said that in the late March or April we shall have some rains, and indeed the rains came. and that's the use of or how important the satellites are. Let's can see what next. Now we must also know, are the satellites only important for weather forecasting only? Can't a satellite be important in other ways? Let's see. So however, the satellite may also be important in the following ways. Yes, one is for surveillance, communication, research, navigation, making phone calls across continents, live broadcasts, and many more. Now just to break down this for the people of Uganda. So for surveillance, because now, like say for example, how is America able to detect some of the terrorists? Okay, how is it able to detect some of the terrorists? It is able to detect using the satellite. The satellite can move around. It has got good cameras which can zoom, and even okay. Now about the surveillance, you all have smartphones, I guess, and they have all ever used Google Maps. That time when you're using Google Maps, it means that you're commanding a satellite. You see that you can use Google Maps and zoom a certain area far away from you. Maybe you are living in Kampala, then you can zoom a place maybe in Soroti, and you really see the real image of the place plus their names. That's you're using a satellite for surveillance. Another way is communication. Yes, now like communication here. So for example, the internet we use. You're searching about something on Google, the satellites control that. Research, they can use satellites for research. Still, this will bring it about to the internet. You can search about anything, like in any via Google. Google also is a search engine connected to the satellite. Okay, now navigation. Say for example, they are having a ship which is moving on the ocean. Say for example, the Atlantic Ocean, which is near the USA. You realize that if they have a ship which is moving from USA to Africa, they can use the satellite to navigate and see how far it has gone, or if it has not got any problem along the way. Then making phone calls across the continents. Yes, this is very true. You realize that for you may be in this place and calling someone in the other place. Why? But we are able to communicate without any wire. So that one works with a satellite. Signals go to the satellite sends back to the person. Lastly, live broadcasts. Now this is where we have the TVs and radios. Yes, you are able to receive those signals from your DSTV, your Go TV, just because of a satellite. So indeed, about this part, the people of Uganda should know that the satellite is very important in many ways stated there. Let's move on. Okay, now maybe I will just have a picture of how a satellite looks like. So in simple terms, that's how a satellite looks like. Yeah, and what you're seeing there is our Earth, and satellite has been set into space. Now a person would ask, well, how does it make it to be up there? So a satellite is able to stay up in the air is because it is powered. Now are you seeing what is on the sides here and here? Those are solar panels. And now remember, up there it is up near the sun almost and receiving too much heat from the sun. So the too much heat from the sun will power up these solar panels and charge the battery, which will make this satellite to continue moving endlessly. So it is powered by the sun using the solar panels, and realize that it can stay there for even 1,000,000 years when it has not got any spoiled. That's simply how we can see the picture of a satellite. Let's now go to something else. Oh, we have answered that already. Oh, sorry, I meant to go back. So finally, we have now moved to item 4. Uneb Uce Physics item 4. Let's go through it. They're saying your sister leaves home for work at 7. Okay, let's summarize this. Your sister leaves home for work at 7:20 a.m. and as a must carries tea in a flask. One morning she needed to prepare tea. she carries, let's prepare tea. So okay, she carries, but remembered that the only water she had in the house was 5 liters. Mark this. The only water she had was 5 liters. The only water she had was 5 liters. Let's proceed. Okay, let's proceed. 5 liters in a saucepan of mass 0.2 kg. Please, you need to underline this. Saucepan of mass 0.2 kg in a deep freezer. On removing the saucepan from the deep freezer, she realized that all the water turned into a block of ice. Oh, sorry. The water turned into ice. It was 7 a.m. Now remember, she has to go for work at 7:20. But she's realizing that the water got frozen. But at this time, it is 7 a.m. So that she's left with 20 minutes. Okay. And she was worried about leaving home late, but decided to heat the saucepan containing the block, decided to heat the saucepan containing the block of ice with her heater. Now her heater is rated 4.22 kilowatts until all the ice turned into water and the water boiled, ready for drinking, like she was. Okay, now here they're providing you with some of the constants, like say for example, the specific heat capacity of a saucepan is 900 joules per Kelvin per gram. Was this a typing error? Oh well, it is 900 joules per kilogram per Kelvin. Please, this is kilogram. 900 joules per kilogram per Kelvin. Specific heat capacity of the saucepan. Oh, sorry, please, you change this. This is meant to be water. This can't be saucepan again. This is meant to be water. These constants, you have them there on the paper. Specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Then specific latent heat of fusion of ice is 336,000 joules per kilogram. That's what we have. But no worries, these ones are always given to you in the questions, so don't need to cram them. So density of water, we have it as that. Boiling point of water, we have it as that. Temperature of ice in the saucepan is that. Okay, task. Determine how long it took your sister to boil the tea. Now, how long it took your sister to boil the tea? We shall now start with this. Okay, determine how long it took your sister to boil the tea. Part B. Part B, explain whether or not your sister was able to leave home for work at 7:20. Now remember, like she realized that the water was frozen in the fridge and it was 7 sharp, so she was remaining with only 20 minutes to do all that work. But now she has a heater. We don't know whether it will work. Now what we are going to do here is next part. Okay, let's see. First of all, let's begin with part A. We're answering part A. How long will it take? So assuming that no heat is lost to the surroundings. Now in science, we always take an assumption in order for some questions to be valid. So we take an assumption that no heat is lost to the surroundings, though we know that in real life heat has to be lost. Now what you must begin with is, much as you want to calculate, remember when you're dealing with the heat, for us you need to know the mass of water, like that. We need to know the mass of water. That's the first thing. We need to know the mass of water. But remember, originally in the question, if you cross check, they gave us the mass of water was 5 liters. So it means that you need to convert these liters here. Now 5 liters, but you know that 1,000 cubic centimeters squared. Rather, cubic centimeters, that's power 3. This is equivalent to 1 liter. Okay, that's equivalent to 1 liter. So therefore, how many would the 5 have? How about 5 liters? 5 liters will have how many of these? And I think the 5 liters will have that 5 divided by 1,000. And now this will give you, okay, 0.005, like that. This is meters, rather centimeters cubed. Okay, let's now proceed and see how that comes about. Let's now go on. Resolve this. Okay, just continue. So volume of water, we need to know the volume of water. So volume of water, we shall need to convert this into meters cubed. And now when you divide this by 1000, it gives you, now this answer, in fact, if you press on a calculator, this answer is the same as this 0.005. That's what it is. Let's proceed. Now from there, we need to know the mass of water. So what shall do? Shall say mass of water is equal to rho v. Now rho v means this one here is a symbol for density. Density, like that. And v is a symbol for volume. So we have volume, volume is here. How about density? Density has been given to us here. We're very keen. Density is here. Density of water is 1000. So already have it in the question. So you get this, the density times the volume. The volume is this times the density. So we get a mass of 5 kilograms. Hope you understand that. Why? Please, all calculations of heat, they require some mass somewhere. And if mass has been given in grams, please you have to convert it into kilograms. That's what you're meant to do. Okay, let's go there and see. Remove this. Okay, good. Now let's proceed. Now, since you have the masses, let's now get this fact. So that heat supplied by the heater must be equal to heat gained by water and saucepan. Now in heat, what you must know is, if you have your heater, say for example, I'm assuming this is our water in a saucepan. So it means that as this is our heater, we shall now proceed and say, now this heater is providing some heat. It's providing some heat like that. So in that, with the heater, since it is giving away heat, with it will lose heat. So it will be heat lost. While the water and saucepan, they will do what? Gain heat. So in that, in heat, when you're dealing with heat calculations, think about two things: heat gained, heat lost. So heat supplied by the heater, that is heat lost. Here we are losing heat lost. Then heat gained, the heat side we are gaining. So heat lost, here heat gained. Now, where is the heat lost? It is a heater. What is which heater? The heater is rated how? It is 4.22 kilowatts. That's how it is rated, like that. But now it means that this heat will be giving out heat energy. Please let us see this. Will be giving out heat energy, and energy in electricity, energy is equal to power times time. Do you see that? So this heater will be giving out energy, and energy is equal to power times time. That is in electricity. Please you need to just memorize that formula. The energy is equal to power times time. Now let's go there and see what is meant to be done. So let's see. So I saying now here we are saying energy. Since the heater gives us energy, we shall see now it is power times time. The power we have it as 4.22. Now this small time t is the one we need, because they said how long. In fact, just to remind your question, they said determine how long it took your sister to boil the tea, so the time we shall get from here, the power times the time gives us that. Okay, let's go and see. Now what must we know still about this? When it comes to ice, alright, good. So let us proceed. So realize that here what you're going to see here is, now we have finished the heat supplied. Let's now the heat lost. Now in here we have a lot. We have what you call what? Ice. In fact, let me begin with water. In fact, let me just write it here. Allow me to write it here. So we have water. That is our water. Now we have what you call quantity of heat. Quantity of heat Q is given by the mass of that substance times C, that is specific capacity, times bracket theta, or sometimes people call it T2 minus T1. That's what we call the amount of heat gained or lost by a certain substance. So like, for example, if I'm dealing with water, that will be mass times specific heat capacity times the temperature differences. Now this will work for water and saucepan. Water and saucepan shall be using that formula of mass times specific heat capacity C times brackets a T2 temperature differences, T2 minus T1. Please bear with me. The saucepan and water, we shall use that method. Then that is for quantity of heat, or the amount of heat required. Then for ice, please, whenever you say ice, it is the mass times L, whereby this L is the latent heat of fusion. Latent heat of fusion. In fact, we got it here. It is here, specific latent heat of fusion of ice. In order for ice to change into water, so long as there is ice, then we use quantity of heat is equal to ml. So quantity of heat is equal to ml. Now therefore, with the expansion I've given, look here, realize that we have, see, we have m, that I is standing for ice. So mass times LOF, this mass of ice times latent heat of fusion of ice. When it comes to ice, to get quantity of heat, it is ml. Now this one here is, this W is for water. Now mass of ice, because the ice gives us the water, then times specific capacity of water times the temperature differences. Why temperature differences? Because before heating it was at 0 degrees. After heating the water was boiling, therefore it was at 100. Now this one we call it our T1, and this one we call it our T2. The difference in temperature is subtract this minus this. That's what is giving us T2 minus T1. And now since they are all in the same container, they are in just this container, it means that they were all at 0 and now they are at the same time at 100. You repeat the same thing here, T2 minus T1, and you put the same values. Now here you're plus the MP means saucepan, the mass of the saucepan times specific capacity of the saucepan, like that. We have everything here. Let's go there and see. Substituting now, remember the power. Okay, now from here we see that the power of the kettle was 4.22, but remember this power was 4.22 kilowatts, but you can't work out in kilowatts. You have to change this into watts. How do you do that? You just multiply by 1000. Why? It's because a kilo contains 1000, so kilowatt, kilogram, so kilowatt to watts, you multiply by 1000, and now we're saying 4.22, which is here, multiplying by 1000, which is here, times T, and there we go. So now substituting this side, so we captured the mass of water as 5, the latent heat of fusion of ice is that, the mass of water still the mass of ice still stands, this C is specific capacity of water. Specific capacity of water. And now times now 100 minus 0. Why 100? Is because water boiled at 100, that is heat to the highest temperature, and frozen at 0 degrees. So 100 minus this. But I've said why are we using this? It's because they are all in one saucepan and experiencing the same temperature changes. Okay, the 0.2 is the mass of the saucepan. The 900 is the specific capacity of the saucepan. Let's go there and confirm. Okay, realize that here from the question they said that 0.2 in a saucepan of mass 0.2. Guess you can see that there. Now the kettle was rated 4.22 kilowatts. I think you can see that. Let's now go back. Let's proceed. Now next is just calculation. Apply this times this will give you that. Those are the results you get, meaning that when you apply this times this you get that, this times this you get that, this times this you get that. Let's proceed. So now this implies that after adding, this implies that when you add this plus that, you get this guy up. But the algebra says divide both sides by this, it will cancel, then divide by this side, so shall remain with the t is equal to a certain value there. So this will be so finally when you divide, you find that t is equal to 900 seconds. But when you try to convert the seconds into minutes, if you try to convert the seconds into minutes, then you'll get 15 minutes. So it will take her 15 minutes. Remember, she started at 7 and she has to arrive at the work at 7:20. So I think 15 minutes is a bit okay, because she will arrive at 7:15, which is some good time of arrival. Let's proceed and see. So she took 15 minutes boiling the water. Let's go and see part B. Part B they were saying. Part B they said, explain whether or not your sister will be able to leave home for work. Yes, it will be yes, because she will be, the water will boil by around 7 after 15 minutes, which will be 7:15 a.m. of which is needed at work at 7:20. Therefore, she will qualify for the work. Okay. So I will say she was able to leave in time by 7:20 because the tea was ready by 7:15. Yeah, as simple as that. Okay, I think let's first of all end there.